Welcome to The Explainer. All right, today we're going to tackle one of my favorite topics in algebra because it's so visual, solving systems of inequalities. We're going to take what looks like a bunch of complicated rules and turn it into a really simple picture. You ready? Let's do this. So, before we even touch the math, let's start with a really basic question. What happens when you have to follow two different rules at the exact same time? Picture this. You're at an amusement park, and there's a ride with a sign just like this. To get on, it's not enough to be taller than 4 feet, and it's not enough to weigh less than 100 pounds. You have to meet both conditions. That idea, right there, satisfying multiple rules at once, that's exactly what we're doing today. And that brings us to the main objective here. When we're solving these systems, we aren't looking for just one number or a single point. Nope, we're on the hunt for a whole region of possibilities, what I like to call the overlap zone. Here's how it all breaks down. We take that first rule, the first inequality, and we shade in every single possible solution on the graph. Any point in that shaded area works for rule number 1. Then, we just do the exact same thing for the second inequality. We graph its line, and we shade in all of its solutions. So now our graph has two different shaded spots. And here it is. This is where the magic happens. The actual solution to the whole system isn't just in the first shaded area, or the second one. It's only in the place where they overlap, the one spot on the graph where both rules are true at the same time. Now, of course, there's a formal math term for this overlap zone. We call it the solution region. And it's pretty cool because you can pick any point you want from inside that region, and you know for a fact it's a valid solution. Okay, enough with the theory, right? Let's actually see this thing in action. We're going to walk through 3 different examples, step by step, so you can see exactly how this works. Let's kick things off with a super common example. Our system has 2 rules. Y has to be greater than x, and y has to be less than negative x plus 4. Let's see what that looks like. Okay, first things first, we graph y equals x. Now, because it's greater than, not equal to, we have to use a dashed line. Then we shade everything above it. Next up, we graph y equals negative x plus 4. Same deal, it's a dashed line because it's less than, and we shade everything below it. And would you look at that? You see that wedge shape where the 2 colors overlap? That's it. That's our solution region. All right, on to example number 2. What happens when our inequalities are just simple horizontal lines? Let's solve the system where y is less than or equal to 3 and y is greater than or equal to negative 1. Now, the key thing to notice here is that we're using solid lines. Why? Because our inequalities have that little or equal to part, which means the lines themselves are actually part of the solution. So we draw a solid line at y equals 3 and shade below, and another solid line at y equals negative 1 and shade above. And the overlap creates this perfect little horizontal strip. Okay, for our last example, let's look at a bit of a trickier situation. What happens when you have a system like this one? Y is greater than x plus 2 and y is less than x minus 1. The first thing you might notice is that both lines have the same slope. And what does that mean? It means they're parallel. They are never, ever going to cross. So we shade above the top line, and we shade below the bottom line. And the shaded areas are actually moving away from each other. They will never touch, which means there's no overlap and therefore no solution. So now that you've got the basic idea down, let's talk about a couple of really common mistakes, just so you know what to look out for and can get these right every single time. Okay, this is probably the number one mistake people make. They stop halfway. Just shading the area for one inequality isn't the final answer. You have to find the region where they overlap. That overlap, and only that overlap, is your solution. And here is a rule you just need to remember, plain and simple. Points on a dashed line are not solutions. Think of a dashed line as an electric fence. It's a boundary, but it's not part of the yard. A point has to be squarely inside that shaded overlap to count, unless, of course, it's on a solid line. So after all this shading and graphing, I know what you might be thinking. When am I ever actually going to use this? Well, let's take a look. The short answer is anytime you're dealing with multiple constraints or limitations at the same time. And trust me, that happens all the time in the real world. Just think about civil engineering. An engineer designing a road is juggling a couple of big constraints. For safety reasons, the road's width, we'll call it W, has to be at least 20 feet wide, but for legal reasons, it can't be more than 50 feet wide. Both of those rules have to be true. And in that situation, the solution region isn't a shaded area on a graph, it's the actual range of possible widths. The road can be 20 feet wide, or 30, or 50, but it can't be 10 feet wide and it can't be 60. That range, from 20 to 50, is the set of all the safe and legal design. So, as you can see, this is so much more than just lines on a graph. It's a really powerful way to think about and solve problems that have multiple constraints. Now that you know how to find that overlap zone, what other real-world problems do you think you could solve? Thanks for watching.